electronics too. Now we are going to present our presentation on RC phase shift oscillation. First, let us consider what is an oscillator. Here you can see the block diagram of an oscillator. Basically, the function of an oscillator is to generate alternating current or voltage waveforms. More precisely, an oscillator is a circuit that generates a repetitive waveform of fixed amplitude and frequency without any external input signal. An oscillator is a type of feedback amplifier in which part of output is fed back to the input via a feedback circuit. If the signal feedback is of proper magnitude and phase, the circuit produces alternating currents or voltages. Now, let us consider the circuit diagram of an RC phase shift oscillator.
Figure shows a RC phase shift oscillator, which consists of an opamp as the amplifying stage and 3 RC cascaded networks as the feedback circuit. The feedback circuit provides feedback voltage from the output back to the input of the amplifier. The opamp is used in the inverting mode. Therefore, any signal that appears at the inverting terminal is shifted by 180 degree at the output. An additional 180 degree phase shift required for the oscillation is provided by the cascaded RC network. Thus, the total phase shift around the loop is 360 degree or 0 degree. At some specific frequency, when the phase shift of the cascaded RC networks is exactly 180 degree and the gain of the amplifier is sufficiently large, the circuit will oscillate at that frequency.
And this frequency is known as the frequency of oscillation, which will be calculated in further parts of our video using theoretical and practical values.
Apparatus required.
Now we require a cutter,
the connecting wires,
a capacitor of 0.01 microfarads,
the resistors of 1 kilo ohm, 1.2 kilo ohm and 50 kilo ohm,
a multimeter to measure resistances and capacitances,
the BNC for finding our output,
a breadboard and a 741 IC.
Here you can see the pinout of the 741 IC.
Now let us perform the experiment of an RC phase shift oscillator. Here you can see the circuit diagram and breadboard. On breadboard we have already plotted 50 kilo ohm, 1.2 kilo ohm, 3 capacitors of 0.01 microfarads and 2 resistances of 1 kilo ohm. Now connecting the 1.2 kilo ohm to the second pin, which is the inverting pin of an opamp. Connecting 50 kilo ohm feedback to the second pin again, which is an inverting pin of an opamp. Now we connect the 50 kilo ohm resistor to the sixth pin, which is the output of the opamp. Now we connect the feedback circuit back to the input circuit, that is connecting the three capacitors and the resistors back to the inverting input. Grounding the third input, which is the non-inverting. Now grounding our entire circuit using the 0 volt. Now we connect our circuit to the plus minus 15 voltage supply, where the minus 15 voltage supply is connected to the fourth pin and plus 15 voltage supply is connected to the seventh pin. Now we connect our oscillator circuit to the output. And finally we connect our BNC cable at the output, which is the sixth pin, in order to get a voltage waveform at CR. Hence our circuit has been prepared. Now let us watch some observations on CR.
Here you can see the output waveform by the RC phase shift oscillator. Let us calculate the time period of the waveform. You consider the distance between a single wave. Here you can see it consists of two blocks. We multiply it with time base to get the time period.
Calculations. Let us calculate the theoretical and the practical frequency of an oscillator. First, let us calculate the theoretical frequency of an RC phase shift oscillator, which is given by a specific formula, which is F is equal to 1 upon 2 pi R C under root 6, where the values of R and C is 1 kilo ohm and capacitor 0.01 microfarads. But when measured from multisim, R is 0.98 kilo ohms, whereas the capacitor is of 0.012 microfarads. The answer we get is the frequency is 5.4 kilohertz. Now calculating the practical frequency. As calculated the time period from the CRO, we got time period is 0.1 millisecond for time base into two boxes, which is 0.2 milliseconds. We get frequency as 5 kilohertz.
Here the multisim of our practical.
Now we bring the 741 IC of an opamp, then we bring a digital ground, and then we connect the third terminal to the digital ground. Then we bring all the resistors at once in our circuit, which includes RF, R1 and two resistors of RC circuit. Then we define the values such as RF is equal to 50 kilo ohms, R1 is equal to 1.2 kilo ohms and respective Rs as 1 kilo ohm. I must tell you that all the components can be brought under the drop-down menu of place. Now we bring the capacitors of 0.01 microfarads, three capacitors of 0.01 microfarads, and then we make our circuit connections accordingly to the circuit diagram. I must tell you again that all the components required in a multisim can be found under the drop-down menu of place. Now we bring the power supply plus VCC and minus VEE. By double clicking on plus VCC and minus VEE, we can define their values and we required them as plus 15 volt and minus 15 volts. Now on the right hand side there are various instruments, among which one is oscilloscope. Then we bring in oscilloscope, we connect its one terminal to the output and to the digital ground, and then we simulate our multisim. Here you can see, in order to get a appropriate waveforms, we bring the scale to 100 microvolt per divisions. Thank you for showing such a keen interest. Credits Astha and Akshay.